In this lesson, we're looking at angle relationships in circles. So I want to talk a little bit about the angles that we've discussed so far in this chapter. We've talked about central angles, where the vertex is the center of the circle and its measure is the same as its intercepted arc. In an inscribed angle, remember, its vertex is on the circle and the measure of the inscribed angle is half of its intercepted arc. We've talked about angles in inscribed quadrilaterals and those opposite angles in those quadrilaterals being supplementary. We've talked about tangents and circumscribed angles and how the circumscribed angle is supplementary to its related central angle. And so now in this diagram we see an angle that is formed inside the circle, not at the center of the circle, but just somewhere inside it. And so your explore activity in this lesson is wanting you to use geometry software like what we have on the screen and measure angle DGF, which I have here, measure arc CHE, measure arc DIF, and add those two arcs together. So here's angle DGF, DGF for some reason isn't labeled. Let's label it. And its measure is this 149.82. And what we're trying to see is a relationship between the measure of the angle and the sum of this arc DIF and this arc CHE. And so notice it looks like it's about, that sum is twice the angle. So let's see if that's always true. So I'm moving the angle around and here's the angle again. Here's the two arcs. There's the sum of the arcs. And sure enough, the angle is half that sum. So as I drag angle G around, notice how all of these measurements are changing, but how this angle is always half the sum of those two arcs. And you see on page 830 that it's asking us, can we make conjecture about the relationship between the angle measures and the two arc measures? And I'll have the written version for you in the next part of the video under the document camera, but a conjecture could be that the measure of an angle formed inside of the circle equals half the sum of the intercepted arc of the angle and the intercepted arc of its vertical angle. At this point, you'll notice that the measurements on the screen are a little bit different. Notice how since this angle is outside of the circle, it is intercepting two different arcs. It's intercepting this arc, arc FBC, which I've measured here, and arc EJD, which I've measured here. Then your textbook in number 2 on page 830 says, find the difference of those arc measures and see if you notice a relationship between that difference and the measure of the angle outside the circle. And what I'd hope that you'd notice is that this angle is half the difference between those two arcs. Now, is that a happy coincidence? Notice that the angle is staying the same, even though the arcs are changing, that difference between them is staying the same. Here you see I'm changing the angle, but still, it's half the difference of the two arcs. Here you see the relationships typed in that were discussed in the first part of the video. You might want to pause your video to jot these down. Here you see the intersecting chords angle measure theorem, which says that an angle formed inside is half the sum of the two intercepted arcs. And here we're proving that theorem. So we have chords AD and BC intersecting at point E that's given to us, and we drew an auxiliary segment BD because through any 2 points there's exactly one line. And then we know that angle 1, measure of angle 1, will equal the sum of EBD and EDB. And the reason for that is the triangle exterior angle theorem. And we haven't used that in a while, so let me clarify that. The triangle exterior angle theorem says that an exterior angle, like angle 1, will equal the sum of its two remote interior angles, which are angles B and D. Then I have that angle EDB is equal to half of arc AB, and angle EBD is equal to half of arc CD. That's the inscribed angle theorem, which says that the measure of an inscribed angle is half of its intercepted arc. And then I substitute in those measures for angles EDB and EBD. So angle 1 will equal half of arc AB plus half of arc CD. And then when I factor that 1/2 out, I have that the measure of angle 1 equals 1/2 measure of arc AB plus measure of arc CD. And that's distributive. So let's use that theorem. Here I'm asked for angle MPK. Let's trace it. It's this angle. It will equal half of the sum of the two arcs, which are KM and NL. So angle MPK will equal half of 61 plus 111. And in my calculator, that's 172 divided by 2 is 86. Number 5, this time I'm asked for arc PR. Notice that angle STQ will equal half of the measure of arc SQ plus the measure of arc PR. So when I substitute those values in, I'm going to do that down here. When I substitute those values in, I have that 58 equals 1/2 of 82 plus the measure of arc PR. That gives me, well, let's multiply the whole equation by 2 so I get rid of that 1/2, because that can be annoying. That'll be 116 equal to 82 plus the measure of arc PR. Subtract the 82 from both sides, and the measure of arc PR is 34. Here we have the tangent secant interior angle measure theorem. Goodness, that's a mouthful. And notice it's talking about the angle formed by a secant and a tangent intersecting at the point of tangency. And the angle ABC, is half of arc AB. Notice where the vertex of this angle is. It's here on the circle. So you could treat this as if it's an inscribed angle, and once again, it's going to be half of the arc that it's eating. In example 2, they're using that theorem. Angle BCD is asked of us, and what we did was take half of arc BC to find the measure of angle BCD is 71. In part B, we're finding the measure of arc ABC. I know that angle ACD will be half of that arc, I also know that angle ACD will be 90 degrees, so that means that the measure of arc ABC is 180. In your turn number 6, I'm asked for arc PN. Notice that arc PN is being eaten by that 61 degree angle, so 61 equals half of the measure of arc PN. So in order to solve for arc PN, I multiply both sides of the equation by 2. So that's 122 is the measure of arc PN. In number 7, I'm asked for the measure of angle MNP. Notice that arc NQP is 238. That means that the measure of angle MNP will be half of that 238. So it's 119. When an angle is formed outside, notice that there's 3 different ways that this can happen. We can have 2 secants intersecting, 2 tangents intersecting, or a secant and a tangent. And it always works out the same exact way. You're taking half of the difference between the 2 arcs that the angle is going through. In example 3, part A, you see that we are using the fact that angle L is half of the difference between 2 arcs in order to find the measure of arc KM, and they found it to be 33. In part B, X is the angle formed outside the circle. It is half of the 2 arcs that it's going through. One of the arcs that it's going through is this 238, and oh no, I don't know this arc. Well, it's got to be 360 minus 238, which is a 122. When we subtract 238 minus 122, we have 116. And when we take half of that, that's 58. In this your turn example, once again, my value of X is the angle formed outside of the circle. It will therefore equal half of the difference between 2 arcs, the larger arc being 161, smaller one is 67. So that'll be 1/2 of 94, which is 47. Here in this example, the circle that you see is an eyeball. There's a muscle on top and a muscle on bottom, represented by segment CA and CB. Arc AEB is 225. I'm asked for the measure of angle ACB. Well, it's an angle formed outside of the circle, so it'll be 1/2 of the difference between 2 arcs. The larger arc is that 225. The smaller arc is 360 minus 225. So that's 1/2 of 225 minus 135, which is equivalent to 1/2 of 90 or 45 degrees. So here we see the relationships between angles and their chords. If the vertex of the circle is on the circle, it's going to be half of the intercepted arc. If the vertex of the angle is inside, it'll be half the sum of its intercepted arcs. If the angle is formed outside, it will be half the difference of its intercepted arc. So in angle 4, now we're taking all these relationships and throwing them together. I'm asked for arc FD. Notice how they're using that angle E is an angle formed outside of the circle, It will therefore be 1/2 of arc BF minus FD, which is the arc that we're solving for. And this is a typo. They multiplied both sides by 2 to get rid of the 1/2, but this would be 150 minus arc FD. So when they subtract that 150 from both sides, that's where they're getting the -50 from, and then they divided both sides by -1 to find that arc FD is 50 degrees. In part B, I'm asked for arc CD. And what they're using here is, well, I know what arc BC is, I know what arc BF is, I just found out what arc FD is. All of the arcs together have to add up to 360, so that's why they're doing 360 minus these arcs that we know. So add up the 64, the 150, and the 50, and that's 264. That we're subtracting from 360, and that means that the measure of arc CD is 96. In number 10, we're finding the measure of arc KN. That's this arc here. So what I notice about KN is that it's being eaten by angle KQN, which is also intercepting this 86-degree arc. So it'd be really convenient if I could find the measure of angle KQN. Well, the measure of angle KQN will equal 180 degrees minus this 79. They form a linear pair. So KQN is 101. When I take that and set it equal to 1/2 of arc JP plus arc KN, now I can find the measure of arc KN. Let's multiply the whole equation by 2 first to get rid of that 1/2. So that'll be 202 equals JP plus KN. JP is 86, so I have 202 equals 86 plus Kn. And when I subtract 86 from both sides, 202 minus 86 is 116. So the measure of arc Kn equals 116.